I have the immense privilege now to introduce Ciara. Ciara has been my co-moderator at Eurorust last year, and it was fun. It was an amazing opportunity, a real pleasure. And she's also not only the moderator of Eurorust, but also the organizer of the Rust and C++ Cardiff meetup, or also known as the Dragons. I heard it's a virtual meetup, so you can tune in anytime. And I heard from Tim Janus that there will be one next week. Is that correct?
Yes, like a hybrid special one. Put up the event tomorrow, hopefully.
Going to be fun. So she's very involved in the community, and she's a wonderful human being. So please give it up for Ciara and to talk about atomics.
Hi, everyone. Thank you for joining me. The next half an hour is going to be my attempt at a crash course in memory ordering. So, as mentioned, my name is Ciara. I'm a software developer at Esri, and we build mapping software. I'm also, as Stefan mentioned, an organizer of an online meetup. As part of that meetup, we had a book club on Mara Boss's excellent book, Atomics and Locks. If you haven't read it, I would really highly recommend it. This talk is very derivative of what we got out of that content. That meetup for me highlighted how many misconceptions folks have about memory ordering. Even experienced developers who'd been coming to the meetup for a while still got muddled up, still got confused. I think this is a topic that a lot of developers struggle with or gloss over. So if you feel like you're guessing whenever you have to put a memory ordering down, or if you've just avoided them entirely because you didn't really understand what they were, then this talk is for you. If you're looking for a bit more of a niche, future-looking aspect of memory ordering, like consume ordering, then this talk might not be for you, might not teach you anything new, so I won't be offended if you switch tracks. We'll start with a little bit of background information, covering the very basics of atomics and lock-free programming. We'll then discuss some of the assumptions that we're allowed to make with single-threaded code, which no longer hold when you introduce multiple threads. We'll look at how memory ordering solves our problem case, and then we'll end with a laundry list of further reading, because this talk is only half an hour, and there is so much in this topic that you can learn. So do check those out if you're interested. So why use atomics, and what are they? Why do we care about atomics? Because most of us have machines with multiple processors, and we want to take advantage of those. Often that involves sharing memory between threads. This is mostly pretty straightforward, especially in Rust. It's fairly difficult to go wrong. You do your thread spawn, you throw your data in an arc mutex that you want to share, and then take care to hold on for that lock for as little time as possible, and then you're good to go. If you're using mutexes for all of your shared data, then you don't need to worry about memory ordering. It's all handled for you under the hood, pretty much. But sometimes you're running in a really hot path of your code, and the cost of locking and unlocking that mutex becomes too expensive. So for a subset of data types, we can instead use atomics. Rust gives us access to these lock-free primitives, which are pretty basic: atomic bool, atomic U32, atomic U64, etc. And all of these we can update from multiple threads in a totally lock-free manner, provided our platform supports them. They're a platform feature, but they're exposed in a platform-agnostic way. So what do atomics give us? Well, as mentioned, they're lock-free. So they're guaranteed to be lock-free. If your code compiles, those atomic operations will be lock-free. That means they don't require a global mutex. We also get no torn reads and writes. So when you've got multiple threads or multiple processes reading and writing to memory, we want to make sure that that write has completely completed before some other thread tries to read from it. Otherwise, we could have partially written data, which might be totally nonsense, and we essentially get undefined behavior. Atomics also provide these read, modify, write operations. So there's a kind of subset of operations that will be able to read from your memory, update the data, and then write it back, all in one single step. So again, there's no way another thread can get in there in between the read and the write and try to write some additional data. It's all done as one atomic, indivisible operation. And this is how that looks. You can read, modify, and write to atomics using member functions like fetch, add. So here we're reading foo, which we've initialized with 5. We're adding 10 to it and storing it back in all as one single atomic operation. To use any of these operations, you have to specify an ordering. And to understand why that's needed, which is like the whole point of this talk, we're going to need to go back to basics a bit and talk about the assumptions that we make when we write our code. We write our code to do what we want it to do. And there's an implicit assumption when we write our code that we want those lines to get executed, and we want them to be executed in the order we write them in. It sounds obvious, but we expect that when we run this, everything will happen one thing after another. In this case, we're creating some null data object, marking that the data has not been set using this isComplete flag. And then we're setting that data and then changing the isComplete flag to true. We read our code from top to bottom. That's the logical order of our code. But what happens after we've written our code is something else entirely. It gets compiled and it gets optimized to be more efficient. And the CPU might shuffle around instructions as well as it sees fit. So even though this is what we've written, that isn't necessarily what happens. But the compiler and the CPU will always make those modifications in a way that looks like our code ran the way it was written. The outputs of the code will be the same as if you had just run the code, just faster. You can think of this as like if a tree falls in the forest and no one's around to hear it, does it make a sound? The only thing the compiler and processor have to ensure is that the end state is the same. And that means some reorders are allowed. They're allowed by the compiler, they're allowed by the CPU. And that means this rearrangement of our code could happen. We've switched the order where we set the data to 7 and set the isComplete flag to true. When you get to the end of the code, everything is in the expected state. We've set the complete flag and we've set the data. Those things have both happened, but the order they happened in was different. Which is fine as long as this is the only code running, but when there's multiple threads in play, this no longer makes sense anymore. The role of that isComplete flag has totally changed. If we introduce a second thread, the data write order on thread 1 suddenly becomes important. If we've set the isComplete flag after we've set the data, we can use it to tell us that the data has been set. So we're relying on that flag on another thread. If we can switch the order, we can get into trouble. We can enter this branch and try to operate on our uninitialized data. So how does the compiler or CPU know that it's not allowed to do this? How can we tell it that this reordering shouldn't have been allowed? Well, without ordering, there isn't really a way to do it. We could imagine that we could tweak the code in thread 1 so that it does have an observable difference if we switch the order, and that might prevent some kinds of reordering. So here we're checking the value before we set the flag, which would in theory change the code such that there's not any rearrangements that the compiler or CPU could make to switch the order of the data set and the isComplete set. As far as thread 1 is concerned, the Boolean is only set to true after the data has been set. And you might assume that now all is well with the world, but unfortunately not. Here I have that same code, which has 2 threads. Again, starting with the data as null and the isComplete flag set to false. I've just changed it to an atomic bool to allow it to be shared. The second thread loops until the isComplete flag is read as true. And only once the isComplete flag is true does it check the data. And at first glance, it looks like this should always succeed. The data should always be set. But if I run it in a loop on my laptop, which has ARM under the hood, then the assert will frequently fail. So how is this possible? The thread only sets the flag to true after the data has been set. So how is it possible that the data is not there and not the value we expect? One way we can think about it is imagining our processor and some memory. Processor 1 is going to be our thread 1. It's going to set the data and then set the isComplete flag. Processor 2 is going to loop, reading the isComplete flag until it reads it as true, and then it's going to read the data and do something with it. So first, we write our data, then we set our isComplete flag, and we're looping until the isComplete flag is true. So we know that this has already happened by the time processor 2 reads the data, because it's set to true, so processor 1 has set it to true, therefore the data has also been set. With this super simple model, it doesn't look like anything can go wrong. But let's say we introduce a cache. The vast majority of CPUs have caches, so this is a pretty reasonable update to our imaginary, pretend, oversimplified CPU. Suddenly, we're not necessarily writing the data and the isComplete flags directly. We might instead be first writing to some intermediate cache, so we can call that data prime and isComplete prime. And those writes happen in the order we expect, but they still need to make it from processor 1's cache to the main memory and into processor 2's cache. And this cache synchronization is totally divorced from our processor order, which means the isComplete flag being set to true could in theory now be read by processor 2 before the data itself is available, which could cause the bug that we saw earlier, that when I ran that code on my machine in a big loop, I got that error. This is the kind of problem that we're trying to solve with memory ordering. So is this how the processor actually works? Is this really the problem? I mean, our imagined CPU there is really simple. Real CPUs are complicated. They may not read individual variables. They might read full cache lines instead. They might reorder the reads and writes in some other way to happen efficiently. Each processor might handle this slightly differently and provide different guarantees about how our data gets synchronized. That code that failed on my machine could very well succeed on yours. Ideally, we don't want to have to know anything about how our processor actually handles memory, how many caches it has, how it synchronizes those caches. But what we do want is for our code to be correct. And for our code to be correct, we need to know that these types of reorders can happen, regardless of why they might happen. Our current best attempt at describing how machine memory behaves generically is the C++20 memory model, and that's what Rust uses. It's very similar to the C and C++11 memory model with a few tweaks. And what it does is it lets us reason about our machine and constrain the behavior without knowing the details. It creates this abstraction. And this is from the doc. It defines the semantics of computer memory storage for the purpose of the C++ abstract machine, or in our case, the Rust. It boils down to this. Out of the box, we have no guarantees about the relative order of different variables we're updating. We've seen that why this might be the case with our imaginary CPU with the caches, but we don't need to know exactly why. We just need to know that it can happen, and we need some way to prevent it or constrain it. This is from a CPP reference. One thread can observe the values change in an order different from the order that another thread wrote them, which is what we observed earlier. We need a way to write our code so that if we read the isComplete flag as true, then we can be absolutely certain that the data was set and that we can read from it. Fortunately for us, we can use memory ordering to do just that. It allows us to create a relationship between the write of the isComplete on one thread and the read of it on another, to ensure that the other data in play has been updated to be consistent with what we expect based on the way we wrote our code and the value of the isComplete flag. We want to know that if we read isComplete as true, then when we read data, it will definitely have already been updated as well. So for that, as mentioned, we use memory ordering. This ordering parameter on store and load gives us a way to describe the relationship between two threads storing and loading the isComplete flag. We fixed it by changing our relaxed store of isComplete to have release ordering, and changing our load of isComplete to have acquire ordering. So let's look at what that means and why it fixes our particular problem. CPP reference says the following about release acquire semantics. If an atomic store in thread A is tagged memory order release, and an atomic load in thread B from the same variable is tagged memory order acquire, and the load in thread B reads a value written by the store in thread A, then the store in thread A synchronizes with the load in thread B. That's quite hard to parse if you're reading it for the first time, so let's break that down. If thread A stores isComplete using ordering release, and thread B reads that updated isComplete value using acquire, then thread A synchronizes with the load in thread B. Now, it's important to say what this doesn't mean is that thread B will necessarily see the update from thread A. All it means is that if it sees that update, then it's going to synchronize with it. If we read the isComplete flag on thread B and it's false, then that means that we didn't synchronize with thread A. If we read the isComplete flag on thread B and it's true, however, then we did read the value set by thread A, and so we synchronize with thread A. Okay, so I've said synchronize with without explaining what synchronize with actually means. What does synchronize with mean? Again, let's take a look at CPP reference. It says that all memory writes, including non-atomic and relaxed atomic, that happened before the atomic store from the point of view of thread A become visible side effects in thread B. If thread A has seen some other memory changes at the point it synchronizes, then thread B must also see those changes. You'll hear this described as a happens before relationship. So now we've fixed our code. Thread A sets the data and then stores true in the isComplete variable with release ordering. Thread B loads the isComplete flag using acquire, and if it reads the value that thread A set, which we know that it does here because it's in a loop, then it synchronizes with thread A. So that means when we synchronize, we get access to all of those data updates from thread 1 that happened before the corresponding release. So I'll leave that up for a second just for people to read it, but that's essentially our fix. A helpful way to think about whether or not release acquire semantics what are needed in your case is to think about what variables in your code can be reordered and still have it make sense. A release store prevents previous memory operations from being reordered to after the store, whereas an acquire load prevents subsequent memory operations from being reordered to before that load. In our case, we require the data to be written before the isComplete write happens. Reordering the data set val call to be after the isComplete store breaks the logic of our code, so we have to use release to prevent that reordering. On the second thread, we require that the data read val operation happens after the load of the isComplete flag. And that's the whole point of this flag, is to tell us that the data has been updated. If we reordered the data read to be before the isComplete flag, then our logic doesn't hold because we're no longer checking the flag. And we can prevent that reorder using acquire. We've essentially enforced the ordering that we had in our simple cashless CPU earlier. On processor 1, the data store can't be reordered to after the isComplete store, and on processor 2, the data read can't be reordered to before the isComplete flag is read as true. Some operations do a load and a store in a single step, so things like fetch add, which we saw briefly earlier. In those cases, you might need to supply acquire release in certain cases, which does kind of two things. It ensures that the load that was used has acquire semantics and the store that was used has release semantics, because we're doing read, modify, write. There's a read there and there's a write. So you're going to have acquire and release. The impact on reordering is the same, only now we might observe acquire and release synchronization behavior in one step, but they still need to have paired loads and stores on other threads for that to make sense, for that to be needed. So that's acquire release. So you can take a breath. These options allow us to prevent reordering by synchronizing a release with an acquire. If you have a release but no acquire, then there's nothing to synchronize with. It also only makes sense if there is other data to synchronize. In our case, we're synchronizing the store and the load of the isComplete flag to ensure that the memory we wrote is going to actually be visible to us. Ooh. But sometimes acquire release isn't enough. And here is one of those cases, lifted straight from Marabos's Atomics and Locks book, which again, you should all read if you could get anything out of this talk at all. So let's walk through it. In this code, each thread has its own guard, A and B, for some string S. We initialize our guards A and B to false and S to be an empty string. Each thread checks whether the other thread has locked the string before writing. If A is true, then thread A is trying to update our string. If B is true, then thread B is trying to update our string. If we're using release acquire semantics, like we are here, then we need to think about what that means. It means when we store true, we release all the memory operations that happened before it on the current thread. But if we look at our code, nothing happened before it. Nothing happened before those stores on the current thread, so it's not really doing anything. And ditto with thread 2, again, that release isn't really doing anything. So can these two pushes ever occur simultaneously? Well, potentially, because A and B are essentially independent. With sequential consistency, they're no longer independent. We get a single total modification order for all of the atomic variables operations that are tagged with sequentially consistent. So what does that mean in practice? It means that both threads have to see the same thing. They have to see the same order. Either A was updated before B, or B was updated before A. There is no way that one thread could see A being set first and then B, while the other thread sees B being set before A. We have some sequentially consistent order across all of our threads that are using this sequentially consistent ordering. This is a much stronger requirement than the happens before relationship of release acquire. And it typically doesn't make sense to mix and match release acquire with sequentially consistent. It becomes much harder to reason about it if you do. But if this is your requirement, if you need all of your variables to happen in a very, very specific order, then sequentially consistent might be what you need. You probably don't, but just in case you do. So do I always need at least acquire release or something stronger like sequentially consistent? No. If I only have one single piece of shared memory, like a counter, then you only need relaxed memory ordering. The other memory options relate to the order of updates to different pieces of data. If there's only one piece of data, the atomic itself, then there's nothing to order with. Even if you do have multiple pieces of data, but they're independent, then again, there's no need to synchronize with some kind of stronger ordering. This might be obvious to some, but I think it bears spelling out. Ordering is only important when there are multiple shared variables with some implied dependency between them. And again, it's worth noting, single atomic variables are still really useful, not least because they are actually completely self-consistent already. Every atomic within itself has a single total modification order. So if I have some atomic and it goes from 0 to 7 to 10, back to 0, many, many operations, every thread is going to observe that same order. It's only relative orders for different data that can vary without synchronization. This is what we were preventing here. In this case, thread 1, the data goes from 0 to 7, and isComplete goes from false to true. On thread 2, the exact same thing happens. The data goes from 0 to 7, and isComplete goes from false to true. It's only the relative order that we observe those changes that's different, and that's what ordering was protecting us with. So relaxed is fine in many, many, many use cases. I wanted to give just an example. If you take arc clone, this uses relaxed memory ordering. This is a very simple example. There is no synchronization that needs to happen with other threads when we're modifying the strong reference count on our arc using clone. Having a single total modification order and the knowledge that there is always at least one other reference, because we have a reference in order to pass it into clone, that's enough. There's no happens before relationship needed. The data inside an arc might be a mutex. We talked about that at the start, how common a pattern that is. And if you're using a mutex, you have already secretly been using release acquire semantics without even knowing it. The lock acquires stores from whoever held it. The unlock releases the current thread stores to the next thread that locks it. Similarly, with thread spawn and join, you don't need to worry about data on the current thread not being visible to your spawn thread. We implicitly have a happens before relationship already. The semantics of mutexes is one of the reasons why it's rare to see issues with memory ordering unless you are also writing unsafe code. Sharing data between threads requires either a mutex or some equivalent wrapper type or unsafe. To be correct, the mutex or equivalent wrapper will already have the kind of release acquire or sequentially consistent, probably not, but release acquire semantics needed to correctly guard your data. And that's ordering. Release acquire creates a happens before relationship between stores and loads on different threads. There are examples where release acquire isn't enough, but they're not very common. We looked at one where we need sequential consistency, which has all the same guarantees as release acquire, but it also creates a total modification order between all the sequentially consistent data. And relaxed has no ordering guarantees, but it does have all of your normal atomic guarantees, such as being indivisible and a single total modification order. So what's the TLDR of this talk? Memory ordering only matters when there are multiple shared variables. And if all your code is safe, it's fairly unlikely you need anything more than ordering relaxed. But you can use reordering operations to reason about what kind of ordering you need. Can the previous stores be reordered after? Can the next reads be ordered before? And you can use that to decide whether acquire or release are appropriate. There is so much online and so many resources available kind of on this topic. Mentioned a few times, Mara's excellent book. I would really highly recommend it if you found this interesting. There's also a series of blog posts by Jeff Pressing, which Amanya, who authored Parking Lot, amongst other things, recommended to me, kindly pointed me at it, and I found them really interesting. They're looking at it from a C++ perspective, but all of the content in there is completely relevant to Rust. There's also the Crust of Rust, John Genset's video on atomics and memory ordering. It's 2.5 hours, but it's well worth a watch. And then there's also things like the C++ standard, the CPP reference. There's tutorials. You can dig into reference manuals if you get really hardcore into it. Don't necessarily recommend that. You don't have to. The Rust documentation alone is enough for most people. But yeah, so I hope you enjoyed that. That is everything I have, and I think I'm about at time.
Thank you so much, Ciara. Amazing talk, lots of information, lots of stuff to catch on to. Are there any questions? So there's a hand up there. Sorry, next one. And also up there, apparently.
Yeah, so I was curious because the talk has been focused now on the semantics, as in, what do I require of my code to do what I want it to? But is that the only consideration for what memory semantics make sense for you? Or, because I presume there's an overhead with the different memory orders. So if I'm just having acquire release, do I just use an arc mutex, or should I be keeping in the back of my mind overhead with the different memory orders?
I would say correctness is the most important thing about your code. And if you're not using unsafe, then probably relaxed is fine for almost all of your use cases. If you're worried about the performance, then, which I assume you are, if you're using atomics, you probably care about performance. But atomics, if you're just doing something like a counter, then you shouldn't be kind of put off by that. Yeah, the performance implications it will be completely dependent on how your code is structured. So it'll depend. But I would say don't worry too much about the performance unless you're actually measuring a problem with your performance. But also don't do sequentially consistent just because you think it's going to be right. Reason about your code. Think is this correct? What I'm writing, does it make sense?
In other words, be relaxed about it.
Yes, be relaxed.
Great. We have another question in the first row. Box coming up. Cool. No interest so far. Great.
So I was wondering, in the first example that you fixed with release acquire, you still checked the value of the data that you wrote before you set the is complete. Is that still something that's required?
No, that's absolutely not required. Yeah. Left it in there to kind of demonstrate the point. The reason that check is in there is to prove that that kind of change is not enough. That was the reason behind that, but it's absolutely not required. Because that's the other thing that acquire release is doing, is it's describing that relationship.
Thank you.
Okay. Any more questions? Over there. Good morning. Cool.
Hi, great talk, thank you. My question is, in the first example, does the acquire and release also guarantee that thread 2 will eventually read the updated value? Or does it just guarantee that if it reads the updated value, it sees all the other stuff that happened before?
My understanding is, the latter. It's only if it reads the updated value and that updated value has come from thread A that it synchronizes with thread A.
Right, so it could still happen that the thread 2 just loops forever if the value never propagates from the cache of thread 1.
For sure, yeah. And in practice, that won't happen, right? Otherwise, but in theory, your thread could never get scheduled, and there's nothing in memory ordering to stop that happening as far as I'm aware.
All right, thanks.
All right, I think we have time for one more question. Let's see if there's a hand somewhere.
I also have a question from the YouTube chat.
Oh, cool.
Philip is asking, how does reordering work with interactive debugging, like with GDB?
Sorry, could you repeat the question?
How does the reordering interact with interactive debugging, with like GDB and stuff?
Oh, interact with debugging. I mean, it's no different, I would say, to any other kind of like optimization. The thing that's causing debugging to be difficult is not the memory ordering; it's the compiler doing strange things. So I don't think there's any special considerations you need to think about.
All right. So if there aren't any more questions, let's have a look around. Then I would say thank you very much, Ciara. It was an amazing talk. Wonderful. Please have another round of applause for Ciara.